So my name is Martin Braniff. I'm from Scotland. I go to Hydrates University, which is located just outside Edinburgh, and is one of the top universities in Scotland for chemical engineering. So my project is based on hydrogen storage in binary hydrates. Now what hydrate actually is basically, it's a cage structure made out of water molecules all joined together, such as the structure here. This is known as structure 2. And it is made up of small cages and large cages. Back. So what we want to actually do is we actually want to try and put hydrogen into these cages so they can be stored there at ambient conditions and then used in applications such as the transport of hydrogen and hydrogen fuel cells and various other hydrogen applications. One of the problems with the pure hydrogen hydrate is though, it forms at about 200 megapascals, which is very high formation pressure and too high for industry. So what we can actually do is we can use promoter molecules such as THF, such as it is shown here. So THF goes into some of the cages and it reduces the formation pressure to about 60 megapascals, which is more acceptable. It's still a bit too high for industry. We still need to try and reduce that formation pressure, but as I say, it's more acceptable than 200 megapascals. One of the problems with THF though is that when it goes into the cages, it actually takes up the space that hydrogen should be taking up. So we actually reduce the weight percentage of our hydrate, which is not what we want to do. So what we can do is we can use what's known as a tuning effect so we basically use less THF, and you can see here, THF takes up less space in the cages, leaving more space for the hydrogen to go into. So the weight percentage of the hydrate actually increases to about 3.6 weight %. This graph here shows the stoichiometric hydrate against the tuning hydrate. So the tuning hydrate here in the green, as you can see, has a higher weight percentage than the stoichiometric one. However, it's still well short of the DOE target of 5.5 weight %. We're showing here about 3 weight % for the tuning sample. The theoretical or maximum for the tuning sample should be about 3.6 weight %. So these results don't actually show the best side of THF, but we're getting pretty close. These results also show the recycling effect of hydrates. So once the hydrate has been used once, if all the hydrogen goes out, we can then reuse the hydrate, put hydrogen back into the cages and effectively recycle that hydrate. So the whole point of these experiments was to show the fact that this is our first time the hydrate's been used, and this is the second time the hydrate's been used once it's been reformed. There you go. However, as I say, the maximum ceiling for THF is 3.6 weight %. We can't really get any higher than that. So THF is going to be put to the side and we're going to focus on the semi-clathrates. Now, a semi-clathrate is basically the same idea. It's made up of these cage structures which we can put hydrogen into. But a semi-clathrate also has a hydrogen molecule as part of the structure of the cage. For example, for this particular semi-clathrate, BH4 is making up part of the structure. We can then use the hydrogen in this BH4 and we can use it in our through a chemical reaction. We can actually release this hydrogen and effectively increase the weight percentage of the semi-clathrate. So before the binary hydrate maximum weight percentage was about 3.6 weight %, but for the semi-clathrate we can increase that weight percentage to about 12.9 weight %, which is well above the DOE target of 5.5 weight %. So for the future experiments, I believe we'll be focusing on the semi-clathrates to try and to prove the concept that they work, to show that hydrogen can be released through another reaction such as hydrolysis, and show that we can actually still keep hydrogen in the cages, and show that we can get about 9 weight % with these semi-clathrates. That concludes my presentation. Thank you for listening.